Hello students, I welcome you in today's session of physics. And in physics, as you know very well, in the our 5 previous lectures, we had covered out most of the topics of this chapter. This is your chapter number 11, and today we are going to discuss about the consequences of escape velocity. Fine. In the lecture number 5, we had already covered what is escape velocity and escape energy. Clear? I hope you understand it very well. Now today we are going to discuss this one. So first we talk about the absence of atmosphere on the moon. What happened? At the moon surface, the value of escape velocity is about 2.38 km per second. Clear? So at the temperature of the moon, the root mean square speed of the gas molecule is more than this value of escape velocity. So you can see here that VRMS means root mean square velocity of hydrogen atom is 2.5 km per second. So the gas molecule have therefore been escaped from the surface of the moon. Hence there is no atmosphere on the surface of moon. Now we talk about black holes. What are black holes? You can see here the second one. So these are the objects having very high density, so that escape velocity from these objects become greater than or equal to the speed of light. So thus even the light particle cannot escape out of it, fine, leading to a dark space. So if the light is sent to such objects, nothing will return back. For an object to be the black body, you can see here root 2 gm by r is greater than or equals to speed of light. Clear? So you can write this expression also, r is equals to or less than or equals to 2 gm by c square, or the black holes are very tiny objects. Clear? Now this is the important topic, orbital speed and period of revolutions of satellites. I hope you are know very well what are satellites. Just as various planets revolve around the sun, in the same way few celestial bodies, celestial means heavenly bodies, revolve around these planets. So these bodies are called satellites. For example, moon revolves around the earth in a nearly circular orbit. In the same way, earth is a planet and moon is a satellite of the earth. So the mass of the earth is nearly 80 times the mass of the moon. Therefore, although earth itself revolves around the sun, but to study the motion of the moon around the earth can be treated to be remain stationary. Clear? Now we will discuss about what is orbital speed of satellite. So when a satellite such as moon revolve in a circular orbit around the earth, a centripetal force acts upon the satellite. I hope you know very well in the chapter of uniform circular motion, I told you about the centripetal acceleration, centrifugal acceleration. Clear? So here you can see any revolving body around any object, always there is a centripetal force or acceleration exists there. So this force is the gravitational force exerted by the earth on the satellite, and from where the centripetal force comes out? It comes out due to the gravitational force of attraction over the body. So you can see here in this figure number 13, this one, a satellite of mass small m is revolving around the earth with a speed v0 in a circular orbit of radius r. So the centripetal force on the satellite is how much? You know very well, mv square by r, where v0 you can see here, this is the orbital velocity. Now let us suppose the mass of the earth is me. You can see here, we suppose the mass is equals to how much? Me. The gravitation force exerted by the earth on the satellite equals to how much? You also know the gravitational force of attraction, gme m by r square, where g is the gravitational constant. So as the gravitational force provides the required centripetal force, so we can write here the force of attraction due to the earth is equals to centripetal force, which is your mv square by r. Fine. So you can see here the small m are cancel out, and the relations comes out to be gme is equals to v0 square into r. Fine. So if you find out the value, you can see that v0 square equals to gme by r. This is the orbital velocity, or you can also write it like this, v0 is equals to root 2 under root gme by r. This is the orbital velocity. Let us suppose re be the radius of the earth and h the height of the satellite above the earth's surface, then the distance of the satellite from the center of the earth will be equals to how much? R is equals to re minus h, this one. Now substituting this value of a small r in the above equation, we have v0 is equals to how much? You will get here v0 equals to gme root under root re minus h. Clear? So if the acceleration due to gravity on the Earth's surface is g, then this relation changes to, you know very well, there is a relation of acceleration due to gravity and gravitational constant gme m into re square, or gme equals to gre square, this one. So we put in place of gme, we can write here, so this orbital velocity, the relation is with the acceleration due to gravity changes. So this is your equation 1 and this is your equation 2, fine. So from the equation 1 and 2 gives the speed of revolution of the satellite in its orbit. So it is evident from these equations the speed of a satellite depend only upon its height above the Earth's surface, fine. Why? Because here you can see g is the constant, radius of Earth is also constant. So greater is the height of the satellite above the Earth's surface, smaller is the speed of the satellite, fine. So because of the speed of a satellite does not depend upon the mass of the satellite, this is important one. So therefore two satellites of different masses revolving in the same orbits around the Earth's surface have same speed. So if the satellite is orbiting very close to the surface of the Earth, then we consider here h is equals to very smaller than the radius of the Earth. So what happened? Then h is negligible compared to the radius of the Earth, and we put here in this formula h is equals to 0. So this comes changes to like this, v is equals to gme by re, or you can also write v naught equals to root gre, fine. So after putting the value of acceleration due to gravity and the radius of Earth, you can easily find out the value of orbital velocity. You can see here the speed of the satellite revolving very close to the Earth's surface is nearly 8 km per second. This is the orbital velocity or speed of satellite which is revolving close to the Earth's surface. I hope it is clear. Now we will discuss about what is the period of revolution. So period, I hope you know the time period, the time taken by a body to complete one revolution around the Earth or any planet. So the capital T be the time of one revolution of the satellite. So you know very well T is equals to 2 pi r by v naught, clear, where 2 pi is the total circumference and v naught is the orbital velocity. So in place of r, we can also write this formula like re plus h if it is moving at a height, at a certain height, fine. Now what we will did here, you can see that substituting we put the value of v naught, clear, from the above expression we put the value of v naught. Then this relation changes to like this, t is equals to 2 pi re plus h upon gme by re plus h to the power half, clear. Or you can also write this expression t is equals to 2 pi root re plus h whole cube upon gme. And you know it very well, there is a relation of acceleration due to gravity and gravitational constant, means gme is equals to g times of re square. So we can write it like this, t is equals to 2 pi in the root re plus h whole cube by gre square. Now there is an assumption, if Earth is supposed to be a sphere of mean density is rho, fine, then the mass of the Earth is given by, you know very well, there is a relation between density is equals to mass upon volume, fine. So from this relation mass is equals to density into volume, clear. So you know you also know the value of or formula of volume of a sphere, which is 4 upon 3 pi r cube. So we from that formula we write this expression and find out the mass of the Earth, which is 4 upon 3 pi re cube and into rho, where rho is the mean density. So if we put this value of mass in the above expression, clear, so what you get, you get the time period is 3 pi re plus h whole cube under root g rho re cube. I hope you understand it. So from the equation, above three equation you can see here, this is your equation number 5. We put the mass of a sphere in equation 5, that's why we get this relation. This is 5th, this is 6th and this is 7th, clear. So equation 5th, 6th, 7th gives the period of revolution of satellites revolving at a height small h above the surface of Earth. It is evident from these equations the period of revolution of satellite depend only upon its height above the Earth's surface. So greater is the height of satellite above the Earth's surface, greater is its period of revolution, fine. That is why which moon which is at a height of this much above the Earth complete one revolution of the Earth nearly 27 days, while an artificial satellite revolving near the Earth's surface complete 10 to 20 revolutions in a day. Here you can see if a satellite is orbiting very close to the Earth's surface, then the height is considered to be very small as compared to the radius of Earth. So in place of h we can put 0 in equation 5, 6 and 7. So you get the time period like this: t is equals to 2 pi root re cube by gme, or with respect to the acceleration due to gravity, the time period is t is equals to 2 pi root re by g. Clear? Or you can also write, if you put the mass in this equation number 9, so this changes to t is equals to root 3 pi by g rho. Clear? Now if you know the value of radius of Earth, find and acceleration due to gravity, so you can easily find out the time period, which comes out to be 84 minutes. So the satellite revolving very close to Earth's surface has a period of revolution about how much? 84 minutes. This is the important one you should remember. And its speed is nearly how much? This thing we had already solved out in the above topic, 8 km per second. I hope it is clear. Here you can see that calculation of mass of Earth. How you calculate the mass of Earth? This one. So we can calculate the mass of Earth by knowing the period of revolution t of an Earth satellite from the equation 5, which we had already described in the above topic. So from there the time period comes out to be like this, and its mass is changes to this. Fine. So if the radius re minus h of the orbit of satellite and its speed or period of revolution is t is known, then from the above equation the mass of the Earth can be calculated. Similarly, if the period of revolution of a planet around the Sun and the distance of the planet from the Sun are known, then mass of the Sun can be calculated. Fine. Now you can see here calculation of height of a satellite above the Earth's surface. If we move or go above the Earth's surface, then what happen? You have to add the height also in the time period. Clear? Or you can find out the value of re minus h whole cube is equals to t square g re square by 4 pi square. Fine. So finally you will get the height equals to how much? This one. I hope you understand it. So thus knowing the t and g and re, the height of the satellite above the Earth's surface can be calculated using this relation. I hope you understand it. Now we will discuss about the geostationary satellite or artificial and polar satellite. Fine. So here you can see that this is the topic. It has been established above that the period of revolution of a satellite depends upon its height above the Earth's surface. Here this is from this relation we can say that. So thus if the height of an artificial satellite above the Earth's surface be such that its period of revolution is exactly equals to the period of revolution, which is 24 hours of the axial motion of the Earth, then the satellite would appear stationary over a point on the Earth's equator. So it would be a synchronous with Earth's spin. You can see here the Earth is rotating about its axis. Such a satellite is known as geostationary satellites or geosynchronous satellites. Fine. I hope you understand it. The condition for a satellite to be geostationary, this is the important one. The first one is the angular velocity or the time period of the satellite should be same as that of the Earth. Clear? Now the second one, the direction of rotation of the satellite should be the same as that of the Earth, anti-clockwise from west to east. Now the third one, the orbital plane of the satellite should be coplanar with the equatorial plane of the Earth. Figure number this one you can see here. The orbit of geostationary satellite is called parking orbit. This is important one. So in order to calculate the height of the geostationary satellite, we use the following expression for the period of revolution of satellite at a height small h above the Earth's surface, which is comes out to be t equals to 2 pi root re plus h whole cube by g re square, where re you know very well is the radius of the Earth. So from the above relation we can find out this expression and this one also. Clear? So if you know the time period of the satellite, radius of the Earth, the acceleration due to gravity, then you calculate the height. So this is the orbital radius of a geostationary satellite. The height of the satellite above the Earth's surface is given by this. So it finally comes out 35830 km. Thus for a satellite to appear stationary, it must be placed in the orbit around each at a height of 35830 kilometers above the equator. This is often called the parking orbit. You have to remember this term. So artificial satellite used for telecasting are placed in parking orbits. The orbital speed of the geostationary satellite, you can also find the orbital speed with this formula, and which comes out to be 3.1 kilometer per second. Now we will discuss about what are polar satellites. So polar satellites belong to another class of satellites. They are low altitude satellites. They orbit the poles of the earth in a north-south direction, whereas the earth is spin around its axis clear in an east-west direction. So hence polar satellite can scan the whole surface of the earth. Since the height of the polar satellite is completely much smaller, which is about 500 to 800 kilometer, so camera fixed on it can view only small strips of the earth in one orbit. Adjacent strips are viewed in the next orbit. Thus the whole earth can view strip by strip. Satellite used for monitoring weather and environment, and the spy satellites are put in the low orbits up to 500 to 800 kilometers. The Indian Earth Resource satellites are polar satellites, this one. So this is the polar satellite. Now this one is the optional launching of artificial satellites. I am skipping this topic. You read it properly. If you have any doubt, kindly ask me in the comment section. And this is the weightlessness of satellite. This is also optional. Further, you can see here energy of an orbiting satellite. This is also an optional subtopic. So I am skipping all this. So from this you can see here, this is the end of the chapter. And if you have any, ask me in the comment section. So from this I am winding the session. Thank you class. Thank you very much.